Hello student, very good morning to all of you. How are you? I hope you all are happy, healthy and fine at home. Do you remember whatever we discussing yesterday? I think yesterday we were discuss about the synthesis of thiophene, and there are two different methods used to synthesize thiophene. One method is a polymer synthesis. For polymer synthesis, he had taken the starting material. He had prepared from 1,4-diketone. The starting compound is taken acetonyl acetone on heating with phosphorus pentaoxide gives 2,5-dimethyl thiophene. And another method, the thiophene can be prepared on industrial scale as follows. On industrial scale, they have taken the starting material N-butane and treated with the 4 equivalent of sulfur, and temperature is kept around 500 degrees centigrade, and the resulting compound obtained will be the thiophene, plain thiophene we are getting. So these are the two different methods we have discussed in our previous lecture. Still one of the method which is represented on blackboard, you can see, you can observe thiophene is synthesized on industrial scale as follows. So this is a N-butane starting material will be treated with 4 sulfur at 500 degrees centigrade, produce thiophene as an end product that we have discussed. Today what we are going to discuss, let us see reactions of thiophene. Let's see here reactions of thiophenes. Reactions of thiophene, that is a point which we are going to discuss over here. Thiophene, reactions of thiophene. And as we know that thiophene undergoes electrophilic substitution at 2 positions. Thiophene undergoes electrophilic substitution at 2 position. I am underlining here, or we can highlight it here, 2 position. Why thiophene undergoes electrophilic substitution at 2 position? How would you justify this? And if you see the electrophilic substitution reaction of any 5-membered rings, generally we have seen so far. Let us see some description regarding why it undergoes electrophilic substitution at 2 position. Everybody knows that the structure of thiophene is this one. Let us see here. This is a structure of thiophene, and thiophene has lone pair on it. And as I already mentioned in my previous lecture that thiophene is more aromatic than the furan. The reason behind it, in furan and the oxygen atom and the sulfur atom, among these two, oxygen atom is more electronegative than the sulfur, and therefore due to the tendency of oxygen atom, it is more electronegative, and due to this tendency it hold the electron tightly than the sulfur atom. Sulfur atom is a bigger atom. The electronegativity of that sulfur is less as compared to the oxygen atom, and due to this reason the valence electron or the outermost electron are more polarizable. In addition to that, the sulfur atom has d orbital, and due to the presence of d orbital it can accommodate negative charge, or it can tolerate the negative charge. The oxygen atom cannot tolerate negative charge on it, and therefore the furan do not shows nucleophilic substitution reaction at all due to the greater electronegativity of that oxygen atom. Now let us see why it gives why thiophene undergoes electrophilic substitution at two position. That the explanation we are illustrating here, we are elaborating here. Let us see. I am showing, this is the arrow. You know that it is a double-headed arrow. Double-headed arrow indicate as a resonating structure. That structure can be interconverted. So this lone pair moving like this or in this manner, then this double bond shifted from here to here, and this double bond shifted here, and the concentrate the electron density at this corner point. So let us see here, this is sulfur. Now 5 membered, what are the changes we made? See here carefully, double bond here, another double bond here, and the negative charge present at this carbon atom. And now look at the sulfur has a 3 bond, and therefore we can put the positive charge on it. It can tolerate as a positive charge because sulfur has d orbital, empty d orbital present over there, and so it can tolerate positive charge as well as negative charge. Now let us see another resonating structure over here. This negative charge forming as a double bond here, and now it pushing the electron density at this corner point, so that we will get the structure. Another structure, I am showing double-headed arrows in a compact manner, means smaller in size, so that we can draw the possible structure, resonating structure of it. What are the changes we made? Look at the arrow here, it forming as a double bond. Now the negative charge present at this corner point, and this double bond remains as it is. Now in the next resonating structure, still this sulfur has a 3 bond, 1, 2, 3, 4, and therefore positive charge still remain on that sulfur atom. Now this negative charge forming as a double bond between these two carbon atoms, pushing this electron density on this corner point, so that we will get the another structure. See here structure carefully. Now this double bond is as it is. What are the changes we made? Here is a double bond. Now the negative charge present at this corner point and still the positive charge present on that sulfur atom. Now look at once again another structure. Now this negative charge, the negative charge, this negative charge forming as a double bond here, and this double bond neutralizing the positive charge in this manner, and we are going to get the next structure, and next structure will be this one, sulfur. What are the changes we made here? Forming as a double bond, lone pair resting on that sulfur atom, and this is a double bond which is forming over here, so that we are getting the structure similar to as the first one. So equivalent to, we can show the structures, or not this one. This double bond is shifted from, not this. Okay, we can neutralize this. So negative charge. So we can represent the resonating structure like this here. Here you can say minus delta charge, here also has a minus delta charge. Look at here. Here at ortho position there will be a negative, as well as this position it will be negative charge. So we can here we can represent this double bond shifted from here to here, positive charge still there, and this double bond forming as a negative charge over here. So let me make that correction so you can remember this one, so that we are going to get the next structure. Next structure would be this one. Now here double bond forming, negative charge over here forming as a double bond, and this is a positive charge still remain on that. And now this equivalent we can look at here at ortho position, at 2 and at 5 position negative charge, at 3 and 4 position there will be a negative charge. So on that basis we can represent the structure. You can show the structure like this. Here is a sulfur, then minus delta charge, here also has a minus and minus delta charge. So still this the lone pair present over there. Now we can show here this way. This is a hybridized structure of this resonance structure of that. And now if you observe these structures carefully, resonating structures, we can number these structures here: first, second, third, fourth, and the last one is a hybrid structures. And that hybrid structure, look at first science structure at ortho position negative charge. Observe the structure number third and fourth. At 3 and 4 position there will be a negative charge, and due to this reason what we can say, this thiophene or the 5-membered ring can undergoes electrophilic substitution at C2 as well as C3, C2 or C5 and C3 or C4. Look at here, partial negative charge present on carbon number 2 as well as 5, carbon number 3 as well as 4, and therefore there is a possibility of electrophilic substitution. This thiophene can undergoes electrophilic substitution. Here mentioning as a 2 position. Why 2? Look at here, if you observe this resonating structure 3 and 4, there is also as a possibility of attacking electrophile at either 2 as well as 4. Equal probabilities are there. But here the one sentence is made, is it true whether the electrophilic substitution reaction occur at 2 position or 3 position? Here already mentioned in previous 2 compound, we already discussed that one. That will be electrophilic substitution preferably attack at 2 position and not at the 3 position. But if you observe these structures carefully, there are 4 canonical structure. They clearly indicate that, and the final structure where you can see at 2, 5 and 3, 4 there will be a negative charge develop on that corners. So there is a probability of attacking electrophile at those position. But why at 2 position? Let us see another way that will give you the answer of this, why thiophene undergoes electrophilic substitution at 2 position. This we can call it as alpha position. This will be a beta position. This alpha, it will be a beta position. And these are the canonical structures. Now, electrophilic substitution shows at 2 position. Why that 2 position? That we are going to look at here. Now I am showing here 2 arrows like this. Here attack at C2 position. This is a C2 position. So 1, because heteroatom always getting as a number 1, 2, 3, 4, 5. So when attack electrophilic, that electrophile attack at, consider or suppose electrophile attack at 2 position, what would be the resonating structure that I am trying to find out? Why electrophilic substitution takes place at 2 position and not at 3 position? That explanation I am trying to give over here. Now when electrophile attack at 3 position, let me show here square bracket. Now here is a thiophene, because we are considering here electrophile hydrogen atom. When electrophile attack at 2 position, what is going to happen? This double bond remains as it is. Here is a positive charge at this position. And now this will be the first resonating structure. Now let us draw. This is a double headed arrow, indicate that resonating structure, one of the structure can be interconverted into as another. These are the, now this double bond, when this positive charge, this double bond shifted from here to here, neutralizing that positive charge, and you will get the structure. That structure I am showing over here. Try to observe this structure carefully. Hydrogen atom here. Here is a double bond. Now the positive charge comes at this corner point. Now let us look at as another structure. Now the lone pair which are present on that sulfur atom, which is involved in a delocalization, it will form double bond neutralizing that positive charge. You will get the structure here. This is a 5-membered ring. Here electrophile and the hydrogen atom we are representing like this. Here is a double bond. Now this double bond here, then now the positive charge present on it. Now I am there is a loss of after losing that proton, aromatization is back. This is the after losing that, forming as a double bond here, this double bond shifted from here to here, and this double bond neutralizing means that lone pair coming on its on that heteroatom, and after that we are going to get the structure. This is a structure. Here the electrophile, double bond here and one double bond here, and this is nothing but as a when the electrophile attack at two position, these are the sum of the resonating structure. This is structure number first, this will be the structure number second, this will be the structure number third, and last step is aromatization. We will get the electrophilic substitution at two position, electrophilic substitution. Now when electrophile attack at C3 position, means which position? This position. If that is there, what is going to happen here? Let's see. When electrophile is attacked, here I am showing, representing, when electrophile is attacked at this position, where the positive charge will be developed at C2 carbon atom, and now we can show as a resonating structure. Now the lone pair which is present on the sulfur atom, they can form the double bond here, neutralizing that positive charge. You will get the structure like this, forming as a double bond here, electrophile hydrogen atom, and this double bond is not participating in the resonance, it remains as it is. Now I am putting that positive charge on that heteroatom, and after that there will be a loss of proton H plus like this. This after losing that proton, forming as a double bond here, neutralizing that positive charge, and finally you will get, this is the structure sulfur. Now here double bond, here double bond, and electrophile is here, right? Electrophile attack at two position. Look at these two structures very closely, very carefully. What do you find? You will find in first case there are three resonating structures are there, but in the second case two resonating structure, and one of the carbon-carbon double bond is not participate in the resonating structure, and due to this reason the electrophilic substitution is less probable, means the electrophilic substitution is not favoring when electrophile attacking at three position, and if the electrophile attacking at the two position, that favor the electrophilic substitution reaction. And due to this reason, I hope you got the answer. What you essentially remember here, two position means thiophene undergoes electrophilic substitution at two position. Why at two position? The answer is here. And if you compare the stability, aromaticity with furan, or even though benzene, that thiophene is more aromatic in nature than the furan as well as benzene. Look at, there are number of resonating structures are there, and if you see in a benzene has only three resonating structure, two resonating structure. So double bond either one or two positions, but here look at the four structures are there, and therefore as the number of resonating structure goes on increasing, the stability of that compound goes on increasing. So in this way we have studied. But thiophene undergoes electrophilic substitution at 2 position. The answer of this here we have seen, because in generalization at 2 as well as at 3 position negative charge are there. So we cannot say whether the electrophilic attack takes place either 2 position or 3 position, because by looking this, by observing this structure, there is a equal probability of attack of nucleophile, attack of electrophile at these positions. But when we draw the actual attack of electrophile at C2 position as well as C3 position and see the resonating structure, in one case when the electrophile attack at 2 position, we are getting 3 resonating structure and aromatization back. But in case of the when electrophile attack at 3 position, we are getting only as a 2 structure and 2 resonating structure. In that, one of the carbon-carbon double bond is not participating in a resonating structure, and therefore this possibility of attack of electrophile at 3 position is a very rare, or we can call it as a very minute or minor case are there, and therefore preferentially the electrophilic substitution occur at 2 position, and therefore this sentence you should remember forever whenever there is a electrophilic substitution reaction in a plain 5-membered heterocyclic aromatic compound. Thiophene undergoes electrophilic substitution at 2 position because thiophene is a more aromatic in nature, and that is the reason why it undergoes as a electrophilic substitution at 2 position. That is the answer we have got over here. And the normal reaction whatever we have seen regarding furan as well as pyrrole, there the 5 common and the general reactions they are showing, just like sulfonation, then Friedel-Crafts acylation, then diazo-coupling reaction, after that Riemer-Tymond reaction, hydrogenation reaction. These are the reactions commonly shown by furan as well as pyrrole. We already discussed in our previous lectures. So these are that reaction will be shown by this thiophene, and that we will going to discuss in our maybe incoming lectures. Here just remember why thiophene is a more aromatic character than the other one, and why it undergoes as electrophilic substitution at 2 position. And for that reason, if you give this explanation, this is a basic explanation regarding that why thiophene undergoes as electrophilic substitution reaction. It is for all whatever heterocyclic compounds are, we have considered if suppose instead of S, if you take as here is a X may be, if you consider X is equal to oxygen, it become as a furan. If X is equal to nitrogen, it will be a pyrrole. If X is equal to sulfur, that becomes as a thiophene. So these are the what we can call it as a different way of representing as a 5-membered ring. And by showing as a energy profile diagram, we can explain why this electrophilic substitution reaction takes place let us see that also at 2 position. Why it favor C2 electrophilic substitution reaction favor this one. Let us see over here. Now with the energy profile diagram, we will explain this one. Let us see here. On x-axis there will be a reaction path, this one, reaction path or reaction coordinate you can call it, and on y-axis you can represent it is a energy, potential energy generally. And now I am showing here one of the graph represented like this. Now another graph which I am showing over here, so like this. Now when this graph, where here let us see general heterocyclic compound, here I am representing X, and here when attack of electrophile. When attack of electrophile at C2 position, let us see here the product is formed. Suppose this is the product, let us say here X, and product is formed. Electrophile attack at 2 positions. See the energy, potential energy is less. In a general way, we know that those organic compound having as a less energy, they are the most stable one. And now when attack of electrophile at here let us say X and electrophile at a position, so this is the energy transition state for what we can call it as a, when electrophile is present. Here X we can show electrophile at this position. We can represent this positive charge over here, and this is the transition state where we can see X, this double bond remains as it is electrophile, and here H is here. So we can partially positive charge we can show over here, that is higher in energy, and from the graph is plotted reaction coordinate versus energy, and that clearly shows that the attack of electrophile at 2 position is favored, whereas attack of that energy from this that disfavored, or it is a less probable. Disfavored you can call it over here. So in this way we have seen why the thiophene undergoes electrophilic substitution at 2 position. By looking at the graph, it clearly indicate that the electrophile attack at 2 position will be a more favored one, and when it is attack at 3 position, that will be a less probable. I think in this way tomorrow we will discuss about the reactions. What are the reactions? Like sulfonation, Friedel-Crafts acylation. These are the reactions we will learn tomorrow. Let us stop today here. Have a nice day. Thank you.